Okay, so today we are diving deep, deep, deep into the world of cubes and cube roots.
Ooh, cubes and cube roots. Sounds a bit technical.
It does, doesn't it?
Yeah.
But trust me, we're going to uncover some really cool stuff today. Like, did you know there's a number out there called the Hardy-Ramanujan number?
Is that like a famous mathematician's phone number or something?
No, not exactly. It's actually the number 1729.
1729. Okay, sounds kind of random.
It does, right.
Yeah.
But it's not random at all. It's actually very special. See, it all started with this mathematician, G.H. Hardy, going to visit his friend, another brilliant mathematician named Srinivasa Ramanujan.
I've heard of him. Wasn't he like a self-taught math genius?
Exactly. Super brilliant. So Hardy goes to visit him, and he mentions that he took a taxi with the number 1729, and he thought it was a pretty boring number.
I mean, it doesn't scream, look at me, I'm interesting, does it?
Right. But Ramanujan, being the math whiz he was, immediately says, no. 1729 is a very interesting number. It's the smallest number that can be expressed as the sum of two cubes in two different ways.
Whoa, hold on. I'm going to need a minute to process this. Two different sets of cubes that add up to the same number?
Yep. 1 cubed plus 12 cubed equals 1729, but also 9 cubed plus 10 cubed equals 1729. Isn't that wild?
That's insane. It's like this hidden code within the number itself I never would have guessed.
And that's what we're doing today. We're diving into a chapter from a math textbook all about cubes and cube roots.
Sounds riveting.
Oh, it is. We're going beyond the basic formulas and looking for those hidden patterns and insights, just like with the Hardy-Ramanujan number.
Okay, I'm intrigued, so where do we start?
Let's start with the basics. What exactly a perfect cube?
A perfect cube. Well, imagine you have a box, but not just any box. This box is perfectly symmetrical, same length, width, and height.
Okay, I'm picturing it like a perfectly square box.
Exactly. Now, a perfect cube is what you get when you calculate the volume of that box.
So, like, if each side of the box is 2 units long, the volume would be 2 times 2 times 2.
You got it. 2 times 2 times 2, or 2 cubed equals 8. That means 8 is the perfect cube of 2.
Okay, that makes sense. It's like the 3D version of squaring a number.
Precisely. And just like squares have patterns, so do perfect cubes. Let's talk about consecutive odd numbers for a second, like 1, 3, 5, 7, and so on.
Okay, I'm with you.
Now, this might seem totally unrelated, but trust me, there's a connection. Think about it. 1 is the first odd number, right? And it's also a perfect cube. 1 times 1 is still 1.
Okay, I see where you're going with this.
Now watch what happens next. If you add the next two consecutive odd numbers, 3 and 5, what do you get?
3 plus 5 is 8. That's the next perfect cube after 1.
Bingo! And it doesn't stop there. 7 plus 9 plus 11 equals?
Let's see, 7 plus 9 is 16, plus 11, that's 27, which is, wait for it, 0.3 cubed.
You're catching on quick. The pattern continues. Add the next 4 consecutive odd numbers, and you get 64, or 4 cubed.
Wow, I never realized that connection before.
It's not just some random coincidence. This pattern reveals a deeper relationship between these seemingly different parts of math.
So those consecutive odd numbers are like the building blocks for making perfect cubes. That's amazing.
Exactly. And what's cool is that this isn't just theoretical. You can actually visualize it. Imagine you're actually constructing a cube, like with building blocks.
Okay, I like where this is going.
You begin with one single block, right? That's your 1 cubed. Now, to build the next larger cube around it, how many more blocks would you need?
Let me visualize it. It would be 7 more blocks.
You got it. 1 plus 7, there's your 8, your 2 cubed. Then to make it even bigger, another layer.
You need 17 more blocks, right?
I've...
It's like those odd numbers are literally building the layers of the cube.
Precisely. Each layer representing those consecutive odd numbers growing towards that perfect cube. It's math you can actually see.
That's incredible. I've never thought about it visually like that. It's like those proofs in geometry, but connecting totally different concepts.
Exactly. Math isn't just these isolated formulas. It's about recognizing these elegant connections, these patterns woven through it all.
Absolutely. So we've got these consecutive odd numbers building up our perfect cubes. Are there other ways mathematicians look at this, like other tools to work with them?
Totally. One of the most powerful tools is prime factorization. Remember how any number can be broken down into a product of its prime factors?
Yeah, like how 12 is the same as 2 times 2 times 3. Those primes are like the fundamental building blocks of numbers, right?
Spot on. Now here's where it gets really cool with cubes. If a number is a perfect cube, each of its prime factors will show up in groups of 3 when you factor it out.
Oh, because to get a cube, you're already multiplying something by itself 3 times. So it makes sense that those prime factors would reflect that.
Exactly. Think about 216, which we know is 6 cubed. Break it down into primes, what do you get?
Let me see. 0.21c is 2 times 1088, which is 2 times 54, which is 2 times 27. And 27 is 3 times 9, which is 3 times 3. Okay, so it's 2 times 2 times 2 times 3 times 3 times 3. Each prime factor shows up 3 times.
There you go. It's like a fingerprint for perfect cubes. If you see those triplets in the prime factorization, you know you've got a perfect cube on your hands.
So prime factorization, it's like a tool to test for perfect cubeness.
It is. And it works both ways. If we see those triplets of prime factors, even without calculating anything else, we know that number has to be a perfect cube.
So perfect cubes have those triplets, and if we see those triplets, we know we're dealing with a perfect cube. Prime factorization, a two-way street to cubetopia.
You got it. And this might remind you of another math concept we often talk about, square roots. Remember how squaring a number and finding its square root are like opposite operations?
Yeah, if you square 5, you get 25. Take the square root of 25, boom, back to 5. So is finding the cube root like hitting the undo button on cubing something?
Exactly. If we cube 4, we get 64. The cube root of 64 takes us right back to 4. It's the inverse operation of cubing.
And there's a special symbol for cube roots, right? It's not just the regular square root symbol, is it?
You're right. We use the radical sign, but with a tiny little 3 nestled in there with it. It looks like this. That little 3 tells us we're specifically looking for the cube root, the number that, when multiplied by itself 3 times, gives us the number under the radical.
Okay, the little 3 makes sense. But actually, finding a cube root seems a bit trickier than just recognizing a perfect cube. Are there, like, methods for cracking the cube root code?
You bet there are. One way is using, you guessed it, prime factorization. Let's say we want to find the cube root of 74,088. Seems like a big, scary number, right?
It does seem a bit intimidating.
But it's not so bad with prime factorization. We break that number down into its prime factors, which happen to be a bunch of 2s, 3s, and 7s, each appearing 3 times.
Wait a minute, that sounds familiar. We've got those triplets again, just like when we were identifying perfect cubes.
Exactly, and that's the key. We've got our prime factors all neatly grouped into triplets. To find the cube root, we just pick one number from each triplet, 1, 2, 1, 3, and 1, 7.
And then multiply those together. So 2 times 3 times 7. That's 42. You're telling me the cube root of 74,088 is 42.
42 it is. Prime factorization helped us reverse engineer that perfect cube. Pretty cool, huh?
That's amazing. It's like prime factorization is the Swiss Army knife of the math world.
Yeah.
But I have to admit, it does seem like it could get a bit tedious, especially when you're dealing with those really big numbers. Is there like a faster way to find a cube root, particularly if we already know it's a perfect cube? I mean, prime factorization is super handy, but yeah, if you've got a massive number, it's a bit like, well, doing things the long way around.
I hear you. Sometimes you need a more direct route.
Exactly. So if we're dealing with a big, bad, perfect cube, is there a shortcut to finding its cube root without the prime factorization detour?
There is. We can use estimation, and it's surprisingly simple once you get the hang of it.
Estimation. With cubes. I'm intrigued. Lay it on me.
All right, let's say we want to find the cube root of 17,576.
Okay, 17,576. Got it. It's a pretty big number. How do we even start estimating its cube root?
It's all about those digits and a little bit of deduction. First things first, we're going to group the digits of our number into sets of 3, starting from the right.
Okay, so for 17,576, we'd have 17 and 576. 2 little groups.
Perfect. Now, that last group, the 576, that one's important. It tells us about the units digit of our cube root.
The units to digit, meaning the last digit. Okay, I'm following.
Right. So we need to think. What number, when cubed, gives us a result that ends in a 6?
It'd have to be a 6, right? 6 times 6. Yeah, that ends in a 6.
Exactly, which means our cube root, whatever it is, has to end in a 6 as well.
Okay, so we know it ends in a 6. That's already something. But what about that first group, the 17? What do we do with that?
That's where knowing our perfect cubes comes in handy. We know that 2 cubed is 8 and 3 cubed is 27, right?
Yeah.
17, it falls right in between 8 and 27.
True.
So our tens digit has to be the smaller number, which is 2.
Hold on. So we're saying that because 17 is between 2 cubed and 3 cubed, the tens digit of our cube root is 2.
You got it. We're using those perfect cubes as landmarks to guide our estimation.
So putting it all together, our cube root is 26.
You nailed it. See, no prime factorization needed.
That's incredible. Feels like we just cracked a code using like logic and a bit of knowledge about cubes.
That's the beauty of math, isn't it? These different concepts, they all connect and support each other.
Absolutely. We've gone from like the very basic definition of a cube to visualizing them with odd numbers, then prime factorization, and now this estimation method. It's amazing how much depth there is to this.
And the best part, this is just the tip of the iceberg. Math is full of these hidden connections waiting to be discovered.
It's like we've unlocked a whole new way of thinking about numbers.
And that's what we're all about here on the deep dive, right? Uncovering those aha moments and seeing the world in a new light.
Exactly. So, to our listeners, keep those mathematical minds churning. We've seen how amazing prime factorization is, how it's practically best friends with perfect cubes. But what about other math operations? Do they have secret handshakes with cubes too? Something to think about. Until next time, happy calculating.